Hi, my name is Nicholas Varghese, and today I'll be presenting my Lab 4 for Physics 21-22. The purpose of this lab was to predict the behavior of circuits containing resistors both in series and in parallel. We will do this by using multimeters to measure the actual values of conventional currents and their potential differences in circuits, and then use these values to examine the behavior of ohmic resistors and capacitors. For this lab, it's important to understand a few basic physics principles and rules, the first of which is the loop rule, which tells us that the algebraic sum of changes in potential around any closed circuit path must be zero. The next is the node rule, which means that at any junction, aka a node in an electrical circuit, the sum of the currents flowing in that junction is equal to the sum of the currents flowing out. It is also important to know the relationship between current and potential, as seen below. Here you will see the setup for this lab. The first part of this lab is a series circuit. Using our circuit construction kit, we took a look at the voltage and currents in a series circuit. We then analyzed the potential differences across the circuit as defined in these locations. The next setup is an RC circuit. For this circuit, we needed a 9-volt battery, 3 different bulbs with different ohm levels, as well as a capacitor and a voltmeter. Using these materials in series, we were able to explore the charge and discharge of a capacitor. We then used the same materials to establish the relationship between time and voltage in the series. Next, we will analyze the results of our series circuit. For part 1 of our analyzation, we will predict what we think the values of the current I1 and I2. To do this, we will solve the equation below. 2 EMF minus I1 times R1 minus I2 times R2 must equal 0. Using this, we can calculate I1 and I2 to be 0.0204. Then, we will then use the circuit construction kit to replicate this model and find I1 and I2. In this scenario, it read out to be 0.02 amps. We will then replace our ammeter with a voltmeter, and we observed the voltmeter read 3 volts. From here, we will observe the potential difference through the circuit. Notice that in the second column, the potential difference sums to 0, as we expect. Next, we can draw a graph of potential versus position. We ask the question, why does the voltmeter not change the ammeter reading even though it alters the circuit? And this is because the impact it has is negligible. Therefore, it does not cause a change in amp reading. We can also ask what occurs when the voltmeter is replaced with an ammeter in parallel with the 100 ohm resistor. In this case, the current would split between a path with 100 ohm resistance and a path with no resistance. This is because it allows the resulting current to be slightly greater than before, as there is less resistance. In this case, the current would be 0.6 amps. Finally, we can find the resistance in the 4 parts of the circuit, using the relationship we defined earlier. As you can see below, in resistor 47 ohms, we get 47.95 ohms. In the 100 ohm resistor, we get 102.05 ohms. In the wire resistor, we get 0 ohms. And the ammeter resistor, we get 0 ohms. Next, we will analyze the results of our RC circuit. In the first part, we used the bulb, capacitor, and battery. In this circuit design, we noticed that the current flowed counterclockwise for a little bit until the capacitor was fully charged and the bulb stopped glowing. In our second design, with only a bulb and capacitor, the current flowed in the opposite direction until the capacitor discharged and the bulb went out. Below, you can see the data from both of these setups. In part 2 of this lab, we used a 30 ohm bulb as well as a capacitor and battery. Here, our voltmeter displayed that the discharging occurred rapidly at first. Then the rate of discharge decreased with time. Current flowed counterclockwise during this discharge. Here you can see our data graphed as a graph of time and measurement. For part 2 of this calculation, the equation from the graph was used to find the RC measurement. We calculated the RC measurement to be 8.547 seconds, and the RC to equal 6 seconds.